Hello there, and welcome to the Sleep Porch. Tonight, we're not just traveling to the largest planet in our solar system, but to the many unusual moons that surround it. Jupiter is not just a single world, but the center of a complex system with dozens of moons, ranging from small captured objects to worlds larger than entire planets. Some are deeply scarred with craters and have remained largely unchanged for billions of years. Others are geologically active, continually reshaped by internal heating, driven by Jupiter's enormous gravity. One holds a planet-wide ocean hidden beneath an icy shell. Another stands as the most volcanically active body we know. Taken together, Jupiter's moons overturn almost every simple idea we have about what moons are meant to be. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, there is nothing else you need to do. Let your body soften. Let the day slowly fade and allow your attention to drift outward as we explore these extraordinary worlds together. Let's begin. Jupiter has more moons than any other planet in our solar system. That means when you look at Jupiter, you are seeing a planet surrounded by an entire community. Some of its moons are large enough to feel like full worlds, with weathered surfaces and deep interiors. Others are small, irregular stones that nonetheless maintain a permanent place within Jupiter's grasp. Together they form a kind of miniature solar system where each orbit is a moving clue about how gravity builds, captures, and rearranges matter over deep time. It also means Jupiter is not just a destination, it is a whole neighborhood. The planet's immense pull acts like a cosmic net, gathering companions and holding them in elegant motion. When astronomers count and confirm new moons there, it is like discovering new islands around a single distant continent. Io is the most volcanically active world we know. If you could stand near Io, the ground would not feel finished. It would feel alive, constantly being remade. Volcanoes there do not just happen once in a while. They are part of the moon's normal breathing, sending fresh material across the surface and replacing what came before. This makes Io a rare place where you can almost watch geology happen in real time, as if the moon is caught mid-creation. Its landscape is painted in dramatic colors because different materials freeze and settle after eruptions, leaving a patchwork that looks nothing like the gray calm of most moons. Io shows how a small world can stay hot, restless, and energetic when gravity keeps squeezing it again and again. It is a reminder that volcanic fire is not just an Earth thing. It can be the heartbeat of a moon. Its volcanoes can erupt for months, reshaping regions again and again. This is not a quick burst and the quiet recovery. It is sustained activity that can keep spilling fresh material, spreading it outward and altering the landscape while the eruption continues. Over time, those prolonged outpourings can cover older deposits, soften or erase small features, and create broad areas that look new compared to their surroundings. It turns the moon into a place where change can be persistent, not just dramatic. If you could watch from orbit, you might see heat signatures lingering in the same locations, like long burning beacons on the ground. That endurance makes each eruption feel like a chapter, not a sentence. It also makes Io a powerful reminder that geology does not always move at a slow crawl. Sometimes it keeps working night after night for months at a time, until a region looks like it has been rewritten. Ganymede may have multiple stacked oceans separated by exotic ice. It is a strange thought that a single world could hold not one ocean, but several arranged like layers in a deep, hidden cake. In this picture, water does not simply sit beneath the surface. It forms a sequence with liquid trapped between different high-pressure forms of ice that do not behave like the ice in your freezer. That means there could be vast amounts of water inside Ganymede, arranged in zones, each with its own pressure, temperature, and chemistry. Even if these layers are separated, the concept still expands the imagination. It suggests that water in the solar system is not always a simple sea with a shoreline. Sometimes it is a buried architecture built by gravity and depth. It also hints that when we talk about ocean worlds, we may be talking about many types of oceans in many layouts, hidden in ways we are only beginning to understand. Ganymede turns the idea of an ocean into something three-dimensional and mysterious. Many outer moons travel backward, hinting they were captured. Most moons form from the same swirling material as their planet, so they naturally move in the same direction. When a moon circles Jupiter the other way, it feels like someone entering a moving crowd against the flow. That backward motion is a strong clue that these bodies did not grow up with Jupiter. They likely arrived later, wandering objects that passed too close and got trapped by gravity during a chaotic era. Capture is not gentle. It tends to leave moons on tilted, stretched orbits far from the planet, as if they are still remembering the struggle of being caught. Over time, those strange paths become a map of Jupiter's past, showing when the early solar system was crowded with roaming debris. These moons turn Jupiter into a kind of collector, holding on to visitors that never meant to stay, and preserving them as evidence of ancient encounters. Some Jovian moons likely began as shattered pieces of larger bodies. When you see groups of small moons sharing similar orbits, it can look like a family, and it might be exactly that. A single larger object could have been captured long ago, then later smashed by an impact or torn apart by collisions within Jupiter's crowded outer neighborhood. The fragments would keep circling, not as a single moon, but as a scattered cluster that still carries the same original orbit, like a shared fingerprint. Each piece is a chapter ripped from a bigger story, now separated and drifting in formation. This makes Jupiter's moon system feel less like a finished museum and more like an active construction site that has suffered disasters and rebuilt itself. The tiniest moons can be clues to the size and nature of bodies that no longer exist. In that way, even rubble becomes a historium, quietly pointing back to a vanished parent world. Jupiter's strongest tides can knead a moon's interior like warm clay. Gravity is not just a force that holds moons in place. Near Jupiter, it can also work like a slow, relentless hand. As a moon moves along its orbit, the pole changes slightly, stretching the body, then letting it relax, then stretching it again. Rock and ice might seem rigid, but over long periods, repeated flexing can make even solid material behave like something that can flow. That internal motion creates heat, not from sunlight, but from constant bending. Heat can open hidden layers, keep pockets from freezing, and drive changes that reach the surface in surprising ways. It is one of the most powerful ideas in planetary science because it means energy can come from motion alone. Jupiter can warm moons without touching them, simply by insisting they keep moving. In that deep, kneading, quiet interiors become active, and small worlds gain the power to surprise. Io's surface can change faster than many landscapes on Earth. On Earth, mountains erode, rivers carve, and coastlines shift, but many features still linger for ages. Io plays by a different clock. Fresh material can spread across the ground so quickly that familiar landmarks can be altered in short spans of time. as if the moon refuses to hold on to yesterday. That speed turns Io into a living map, where change is the default. Imagine returning to the same region and finding that a new flow has covered old ground, or that a bright deposit has faded under newer layers. The surface is not only shaped by violent moments, but by the steady accumulation of new coatings that settle and transform the scene. This makes Io feel intensely present, as if it exists in a constant. Now, for a viewer, it is thrilling, because it proves that geology can be fast, not only slow. A moon can rewrite itself with an urgency we rarely associate with worlds. Europa's ice may float atop liquid water, warmed from below. If you picture Europa as a simple frozen bore, it stays interesting but distant. If you picture it as ice riding on an active sea, it becomes immediate. Floating ice suggests movement. It suggests buoyancy, fractures that can open and close, and slabs that can shift like slow rafts under invisible pressure. Warming from below hints at gentle rising currents where slightly warmer ice becomes softer and creeps upward, while colder material sinks, stirring the shell over time. That is the kind of process that can create patterns on the surface without needing weather or sunlight. It also makes Europa feel layered in a way that invites curiosity. What is the ice doing right now? Where is it thinner? Where is it being pushed from beneath? The most captivating part is that the warmth does not have to be dramatic to matter. A steady, hidden heat can keep an entire moon from becoming silent and can turn a frozen exterior into a shifting skin. Callisto's ancient crust might conceal a deep, salty ocean. Callisto often seems like the quiet one, a moon that mainly records impacts. But even a calm surface can hide a secret. Evidence points to the possibility of a conductive layer below, which is exactly what salty water provides. Salt matters because it lets an ocean respond to magnetic environments, leaving subtle signatures that spacecraft can detect without ever seeing the water directly. It is a wonderfully indirect kind of discovery, like hearing a distant room through a wall and realizing it is full of motion. If Callisto does hold such an ocean, it reshapes the moon's personality. It becomes not just an ancient shell, but a world with a buried interior that still has depth and chemistry. The ocean would be sealed under ice and rock, protected from the most violent space conditions, and preserved for vast spans of time. Callisto then becomes a reminder that stillness on the outside does not guarantee emptiness within. Ganymede's auroras subtly sway with its magnetic environment. Auroras are usually thought of as a planet's light show, but on Ganymede, they become a scientific whisper. Because this moon has its own magnetic space, charged particles can be guided into polar regions, creating glowing bands that shift position. When Jupiter's powerful magnetic field washes over Ganymede, it can tug at those auroral patterns, making them rock back and forth in a way that researchers can measure. That gentle swaying is not just pretty, it is a clue that invisible forces are interacting above the surface, and that Ganymede is not simply sitting inside Jupiter's environment, but pushing back with its own. Observations have even turned those movements into hints about what might be hidden below, because the way a magnetic system flexes can be affected by conductive layers deep inside. So the auroras become more than light. They become a moving diagram in the sky, tracing relationships between space, magnetism, and the moon's interior with every subtle shift. Jupiter's radiation can paint moons with strange chemical stains. Around Jupiter, space is not empty and calm. It is busy with energetic particles that can strike a moon's surface like a constant, invisible sandblaster. Over time, that bombardment can alter materials, changing colors and creating new compounds in the uppermost layers. It is one reason some regions look darker, brighter, or oddly tinted compared to what raw ice or rock might look like on its own. This process is not just cosmetic. It can change how a surface reflects light, how it holds on to thin gases, and how it evolves with time. It is like a cosmic chemistry set running in slow motion. The moon is being edited from above, not by weather, but by particles racing through Jupiter's domain. For a viewer, the fascination is that the environment itself becomes an artist using radiation as a brush. Even without volcanoes or winds, Jupiter's neighborhood can still rewrite the face of a moon, leaving stains that tell you where the harshest space conditions have been at work. The Galilean moons may have formed from a disk around Jupiter. Long ago, Jupiter may have been surrounded by a swirling disk of gas and dust, a smaller version of the disk that formed the planets around the Sun. Inside that circumplanetary cradle, material could clump, grow, and compete, building moons the way planets are built, but on a different scale. This idea helps explain why the largest moons feel like a system with structure, not a random collection. In a disk, there can be regions where rock dominates, farther zones where ice becomes more available, and pathways where newborn moons drift and settle into stable places. It is a beautiful concept because it turns Jupiter into a miniature architect, building its own set of worlds while the solar system was still young. It also makes those moons feel more like siblings than strangers, sharing an origin story closely tied to Jupiter's earliest moments. When you picture that disk, you are imagining a time when Jupiter was not just a planet, but a creator of worlds. Amalthea is strangely low in density, almost as if it were made of porous rubble. That is unexpected so near to Jupiter, where you might assume dense, solid rock would dominate. Instead, it suggests a moon constructed like a loosely packed snowbank, filled with empty spaces inside. Imagine something that could be gently compressed in your hands, if gravity allowed. One explanation is that it formed farther from Jupiter, where colder materials and gentler conditions allowed soft, fluffy mixtures to persist. It may then have migrated inward or been nudged into its current position, carrying that fragile structure with it. Another possibility is that it is a collection of fragments reassembled after an ancient breakup, never compacted into a single hard body. Either way, Amalthea tells a delicate story within a harsh and unforgiving neighborhood. It shows that even near a giant planet, a moon can remain strangely light, like a relic from a calmer, colder corner of the early solar system. Jupiter's moon family includes tiny objects no bigger than a mountain. Some of these moons are more like moving mountains than proper moons. They can be only a few miles across, dark enough to vanish against space, and yet they still hold stable orbits around the largest planet. Finding them is like trying to spot a drifting pebble beside a lighthouse from an ocean away. Astronomers often confirm them by watching faint dots slide through starfields night after night, then proving the same dot returns again and again on the Jupiter-shaped schedule. Their shapes can be lumpy and awkward because their gravity is too weak to pull them into spheres. In a sense, Jupiter turns leftovers into citizens. Even small scraps can become permanent members of a grand system, reminding you that in space, size is not what decides whether something matters. The 4 Galilean moons are worlds you can spot with binoculars. That simple fact is quietly mind-bending, because it means a person standing in a backyard can witness another parrot's miniature system with their own eyes. You are not seeing a photograph or a simulation. You are seeing real worlds separated from you by unimaginable distance, yet bright enough to be caught by a small lens. Over the course of a few nights, those pinpoints will change position, slipping from one side of Jupiter to the other, like tiny dancers keeping time. It is a gentle demonstration that gravity has structure and that the universe is not static. Long before spacecraft, this little arrangement in the sky offered a direct, visible hint that not everything revolves around Earth. It can feel like the heavens are whispering proof that there are other centers, other circles, and other stories unfolding beyond ours. Io's lava can be hotter than many terrestrial volcanoes. That heat is not just a statistic. It changes what lava can do. Potter flows can stay runny longer, spread farther, and reshape terrain in ways that feel more like pouring metal than oozing rock. It also hints at deep conditions inside Io that are intense with melting that reaches temperatures that challenge our everyday sense of geology. When scientists infer such heat, they are reading the glow of active regions and the behavior of eruptions. Like detectives studying a fire by its color, the result is a moon that feels extreme, even by volcanic standards. It is not simply active. It is powered in a way that pushes molten rock toward a fiercer state. That makes Io a laboratory for understanding how heat moves through a small world under relentless gravitational stress. For a viewer, it is thrilling because it means the solar system contains lava that can outdo Earth's hottest seams on a moon circling a giant planet in the dark. Io's colorful surface comes from sulfur and sulfur dioxide frost. Instead of one steady ground color, the moon wears vivid patches that look freshly painted because its surface is constantly being coated and recolored by what eruptions release. Sulfur can settle in different forms, and those forms can shift in appearance depending on temperature and how recently they were laid down. Sulfur dioxide can also freeze onto the ground like a strange alien snowfall, brightening some regions, then thinning or moving as conditions change. The result is a world where color is not decoration. It is evidence, like a map that shows where materials have traveled and where they have recently arrived. When spacecraft look at Io, they are not just seeing pretty pigments. They are watching a chemical landscape in motion, where the surface acts like a canvas that keeps getting reset and repainted by the moon's own activity. Io's thin atmosphere is constantly rebuilt by volcanic outgassing. Imagine an atmosphere that is not a permanent blanket, but a temporary breath that comes and goes with eruptions. When volcanoes release gas, a faint envelope can form around the moon, only to be stripped, frozen, or dispersed by the harsh environment near Jupiter. That makes Io feel less like a world with stable air and more like a world that keeps trying to create air from scratch. It is a delicate cycle where geology becomes weather, and the ground itself supplies what little sky exists. This also means that changes on the surface can quickly affect the atmosphere because the source is right there at the vents and hot regions. For scientists, that connection is thrilling because it lets them link visible activity to a changing envelope above it. For a listener, it is a reminder that atmospheres can be fragile, and that even a moon can have a sky that is renewed by fire. Europa likely hides a global ocean beneath its ice shell. That idea changes the meaning of the word ocean, because this one would be sealed under a lid of ice in permanent darkness, circling a giant planet. Yet it could still be a true sea, stretching around the entire moon, moving with tides pressing against rock below. If that water touches a rocky seafloor, it becomes more than a curiosity. It becomes a place where chemistry can stay busy for a very long time, mixing minerals, warmth, and motion in the same container. Europa's surface, with its long fractures and shifted plates, hints that the ice is not just sitting there like a frozen statue. It may be interacting with what lies beneath, opening and closing pathways over time. In a universe that often looks dry and empty, Europa suggests that hidden oceans might be common, quietly waiting under cold skins of ice. Ganymede is the only moon with its own magnetic field. A magnetic field is like an invisible shield and a signature at the same time, and Ganymede carries one around itself, even while living inside Jupiter's enormous magnetic environment. That means this moon has an active interior with enough structure to generate a field, like a world that never fully went quiet inside. It also means space around Ganymede is shaped into its own little bubble, where charged particles move differently than they do nearby. Imagine a moon that can carve out its own magnetic space while orbiting a planet famous for its powerful magnetism. It is a strange kind of independence. This makes Ganymede feel less like a passive satellite and more like a small planet with its own hidden engine. When future missions study that field closely, they are not just measuring magnetism. They are listening for clues about what is moving deep inside, far below the surface we can see. Callisto is so cratered, it preserves some of the oldest surfaces. It looks like it has been sitting quietly for ages, letting the solar system leave its marks without erasing them. Each crater is a record of an impact, and together they form a surface that feels like an archive. On many worlds, internal activity can smooth things over, burying scars and rewriting the story. Callisto seems to have done far less of that. It is the kind of place where time stays visible. If you traced the overlapping circles and bright rings, you would be reading a history written by collisions, one after another, across immense stretches of time. That makes Callisto valuable in a surprising way. It is not exciting because it changes quickly. It is exciting because it barely changes at all. In a solar system that constantly reshapes itself, Callisto may be one of the best places to see what the early chaos looked like, preserved in plain sight. The Galilean moons orbit in a gravity-locked rhythm called resonance. This is the kind of pattern that sounds like music when you really picture it. These moons do not simply circle Jupiter independently. Their orbits are linked so that each one's timing helps shape the others, keeping the whole arrangement steady and repeating. Resonance is gravity doing choreography, turning motion into a long-lasting relationship over vast timescales. That rhythm can maintain order where you might expect drifting and disorder. And it can also feed energy into the system in subtle ways. It is one of the reasons these moons are so scientifically revealing, because you can see how simple, repeating motion can have huge consequences for a world's interior and surface over time. There's something quietly beautiful about it. Jupiter is not just hosting moons, it is conducting them. The result is a pattern that has endured so long that humans can measure it now and still find it faithfully keeping time. Europa's cracked ice suggests constant reshaping from tides. Its surface does not look like a calm, frozen pond. It looks like ice that has been stressed, pulled, and shifted until it fractured into long, wandering lines. Those cracks are more than decoration. They are evidence that Europa is flexing. As it orbits Jupiter, gravity changes its pole slightly. And that repeating squeeze can make the ice shell bend and strain. Over time, bending turns into breaking. And breaking turns into a surface that records motion like a slow-moving map. Some regions appear jumbled, as if the ice broke into pieces, drifted, and then froze back together in a new arrangement. That idea is gripping, because it means Europa's surface might be communicating with what lies below. Not necessarily by opening wide holes, but by constantly working the same ice again and again. Europa is an icy moon, yet it behaves like a place still under construction, shaped by a tide you cannot see. Io's volcanoes can launch material hundreds of kilometers high. That scale is hard to hold in your mind, because it turns a volcanic eruption into something closer to a space event. On Io, an eruption can throw material so high that it rises above the curve of the moon itself, briefly hanging in the thin environment before falling back as fresh ground. Those towering plumes can spread a wide blanket of new deposits, changing the color and texture of large regions without needing a river or wind. The moon is small, but the eruptions are enormous, as if the planet Jupiter is squeezing Io like a stress ball, and the pressure has to escape somewhere. The result is a surface that refuses to stay the same. You can picture a world where the landscape is repainted not by seasons, but by bursts of molten power. Io shows that volcanism is not only about making mountains, it is about throwing a piece of a world into the sky again and again until the surface becomes a living canvas. Mate's orbit so close, it helps shape Jupiter's faint rings. It moves in a region where the planet's gravity is intense, and the space around it is busy with tiny grains. Those rings are not bright like Saturn's. So, the very idea that a small moon can help maintain them feels like discovering a hidden mechanism. Mate acts like a shepherd by its mere presence, guiding nearby dust through gravity, keeping some particles from drifting away too quickly, and influencing where the ring looks denser or thinner. It is also constantly being peppered by micrometeoroids, and every tiny hit can knock loose fresh material that joins the ring like a quiet donation. So Mate is both sculptor and supplier, a moon that helps keep a delicate structure alive. When you imagine it racing around Jupiter in just hours, you start to feel how dynamic this ring region is. Jupiter is not just wearing rings, it is continuously rebuilding them. Adra also grazes the ring region, feeding dust into it. This moon is so small that calling it a world feels almost generous. Yet its role is outsized. In a place where sunlight, impacts, and Jupiter's pull are always at work, dust does not stay put for long. It needs replenishment, like a faint fire that would go out without new fuel. Adria helps provide that fuel. Tiny collisions can chip its surface, lifting grains into orbit where they join the ring system. Over time, that turns Adrastea into a kind of slow fountain, not of water or lava, but of fine powder released grain by grain. The ring becomes a record of countless little events rather than a single dramatic origin. There is something mesmerizing about that scale. A moon smaller than many earthly cities can help maintain a planetary feature visible across space simply by enduring impacts and shedding dust into Jupiter's shadowed halo. Some moons are dark and reddish, like captured outer solar system objects. Their color is not just a look, it is a clue, suggesting materials that formed far from the warmer inner regions where brighter ice and rock dominate. Reddish tones often point to complex surface compounds that can survive in colder places and darken over time. When you place those moons around Jupiter, they feel like visitors that brought their home chemistry with them. Their odd colors can also hint at long exposure to space weathering, where radiation and impacts slowly change what lies on the surface. The result is a moon that looks almost scorched, even if it has never been near the sun's heat in any meaningful way. These shadowy satellites make Jupiter's system feel like a crossroads. Not everything there originated nearby. Some bodies may be arrivals from distant reservoirs of leftover material, captured and held, carrying faint traces that hint at where they once wandered before Jupiter claimed them. Several of the outer moons gather into clusters, as if born from ancient breakups. When multiple moons share similar distances, tilts, and directions, it begins to feel less like coincidence and more like debris with a common source. Picture a single captured object arriving long ago, then shattered by an impact. The fragments would continue along related paths, drifting apart, yet still circling Jupiter together as a loose family. That perspective turns the outer moon region into a graveyard of old accidents, where today's moons are the survivors of events no one ever saw. Each cluster becomes a question to solve. How large was the original body? What struck it? How long ago did it occur? With time, the fragments may spread and separate, but their shared origin remains written in the mathematics of their orbits. It is an eerie thought that Jupiter's farthest companions may be the crumbs of vanished worlds. The moon clusters become fossil evidence, proving that even in deep space, collisions can rewrite entire populations. The Himalaya group likely shares a common parent, shattered long ago. This is one of those discoveries that makes the solar system feel personal, like you're tracing a family tree rather than measuring rocks. These moons travel on related paths, suggesting they were once part of a single captured body that broke apart. The parent would have been larger, perhaps irregular and dark, and it would have carried a history from wherever it formed before Jupiter claimed it. Then, a violent event, likely an impact, cracked that story into pieces. What remains now are separate moons that still circled together, spread out like siblings who moved to different towns but kept the same surname. Studying such a group helps scientists reconstruct the unseen past, estimating how energetic the breakup was and how the fragments dispersed. It also shows that Jupiter's system is not finished. The outer regions are shaped by loss and rearrangement, and the Himalaya group is a lingering signature of a catastrophe that still echoes in their shared motion. Ara is part of that family, circling far from Jupiter. Its distance gives it a different kind of quiet, a region where the planet's pull is still dominant, but the neighborhood feels wide and spacious. Being far out also makes Ara a keeper of slow stories, because each orbit takes a long time compared to the tight, fast paths of the inner moons. That slow pacing can make its motion feel stately, like it is patiently tracing a route drawn in the solar system's early years. As a member of the Himalaya family, aura also carries the idea of inheritance. It likely shares composition and origin with its relatives, meaning it is one shard of a larger object that no longer exists. When you picture aura, it becomes less about a single moon and more about the event that created the whole group. Aura's orbit is a surviving thread from that ancient break, stretched out across space, still looping Jupiter as proof that capture and collision both leave long shadows. Lisa and leaders share similar paths, like siblings in space. This pairing is fascinating because it shows how astronomers can spot relationships without ever touching the objects. Their orbits are like matching footprints, implying they came from the same source and were set loose together. That shared path suggests a common past, possibly a breakup that produced multiple fragments that never fully drifted apart. Yet even with similar roots, each moon can still be its own character, shaped by slightly different sizes, spins, and histories of impacts. It is like two stones from the same cliff, one chipped smooth, the other left jagged. When you watch the idea closely, it becomes a story about how families can form in space. Not by birth in the usual sense, but by catastrophe, followed by long companionship. Their shared motion also reminds you that Jupiter's outer realm is not random. Patterns exist, and those patterns let us reconstruct events that happened when the solar system was young and crowded. Two faint moons can act like a breadcrumb trail back to a vanished original body. Pasifi's group follows tilted, chaotic orbits that defy neat order. These moons do not sit politely in the same flat plane as Jupiter's main system. Their paths are slanted and restless, like they entered the scene from an entirely different direction. That tilt is important because it suggests capture, not local formation, and it hints at a violent past where objects arrived on unstable trajectories. Over long times, the Sun's pull and Jupiter's gravity can tug at these distant moons, slowly stirring their orbits and making them more unpredictable than the inner, well-behaved satellites. It is a reminder that space has weather, not of air and clouds, but of gravitational influences that can gradually twist paths. The Pasifi group feels like a rough neighborhood on the edge of Jupiter's domain, where the rules are looser and the histories are stranger. Thinking about it can make your skin prickle a little. These moons are evidence that Jupiter's system includes not only elegant harmony, but also a wild frontier where captured objects still carry the drama of their arrival. Sinope moves alone in a distant loop, a loner among captures. Unlike moons that clearly belong to a clustered family, Sinope stands out, as if it never found a group to travel with. That solitude is intriguing because it suggests a unique capture story. Perhaps it arrived at a different time, from a different reservoir of objects, or on a trajectory that did not lead to a larger swarm of fragments. Its orbit is far enough that the solar system's larger gravitational influences can tug at it, making its long-term history feel like a balancing act between Jupiter's claim and the wider pull of space. Being a loner also makes Sin feel like a clue with fewer supports. With a family, you can compare siblings to guess the parent body. With Sinope, the moon itself is the entire evidence. That makes it a kind of mystery stone circling in the dark, quietly insisting that Jupiter captured more than one kind of visitor. Some came with relatives. Some arrived alone and stayed that way. K's group has unusually red surfaces, suggesting similar origins. It hints that these bodies may have come from the same parent object, one that carried a particular mix of materials before it ever met Jupiter. When that original body broke apart, its fragments kept the same basic surface recipe. So even after ages of exposure, they still resemble one another. The color also matters because it helps astronomers separate one group from another in a crowded outer system where many moons are faint and hard to track. It is a rare moment when appearance becomes evidence. The calm group feels like a batch of chips from the same stone, scattered into orbit, yet still recognizable. In a place where most things look like anonymous specks, a consistent color becomes a clue you can follow, leading backward to a single ancient visitor and the collision that turned it into a whole collection. Ansa's group orbits backward like a captured swarm. A backward orbit around Jupiter is like a salmon swimming upstream through a rushing river. It is a strong sign that these moons did not form beside Jupiter in a tidy rotating disk. Instead, they likely arrived from elsewhere and were caught one by one into a shared backward motion. The Anorami group makes that captor story feel even more dramatic, because it is a swarm, not a single lonely object. Their related orbits suggest they are connected. Perhaps fragments of a captured body that later shattered, leaving a flock of moons moving the wrong way together. That image is powerful because it turns Jupiter's outer space into a place with history and tension. These moons are not simply circling. They are survivors of an encounter, still traveling on paths that remember the direction they came from. Every time they complete an orbit, they replay that ancient mistake of direction, and it keeps working. Jupiter's moons include irregular shapes that barely qualify as spheres. When a moon is large, gravity pulls it toward a round shape, smoothing rough edges over time. But Jupiter's smallest moons can be too weak for that, so they remain lumpy, angular, and frankly strange. Some look more like potatoes than worlds, with uneven silhouettes that suggest they were never melted into a tidy form. That irregularity is not just cosmetic. It tells you these bodies are often primitive leftover building blocks that never grew up. Their shapes also affect how they spin, how sunlight warms them, and how impacts carve them, because ridges and slopes behave differently than a smooth globe. There is something wonderfully humbling about that. Not every moon is a majestic sphere hanging in space. Some are misshapen survivors held in orbit simply because Jupiter's gravity is strong enough to keep almost anything. They are reminders that the solar system still contains raw, unfinished pieces. Many small moons spin unpredictably, tumbling instead of rotating smoothly. A smooth rotation feels orderly, like a lighthouse turning at a steady pace. Tumbling is different. It is closer to a tossed stone, rolling and flipping in ways that can change over time. Small moons often do this because their shapes are uneven and their gravity is weak, so nothing forces them into a calm, consistent spin. Past impacts can also leave them with odd rotations that never fully settle. That means their day and night patterns can be strange, with sunlight striking unexpected regions, then vanishing as the moon turns a different face. If you could hover nearby, the horizon itself would feel unreliable, as if the ground cannot decide which way is up. This makes these moons feel alive in a nervous, jittery way. They are not serene worlds. They are rotating relics still carrying the momentum of ancient hits and close gravitational nudges. Their tumbling becomes a physical memory stored in motion instead of stone. Some orbits are so stretched they swing dramatically in and out. A stretched orbit turns a moon's journey into a long breath, moving close to Jupiter for part of the cycle, then drifting far away for the rest. That back and forth changes everything about its experience. Near Jupiter, the moon races faster, feels a stronger paw and passes through a different environment than it does at its most distant point. Far away, it slows down and spends long stretches in the outskirts, where space feels less dominated by the planet. This kind of orbit is a hint of a rough past, because gentle formation tends to make calmer, more circular paths. Stretched orbits often point to capture, collisions, or gravitational reshuffling. They are the footprints of disruption. For a listener, the wanderer is imagining a moon living two lives, one as a near neighbor and one as a distant wanderer, repeating that swing endlessly. Its orbit becomes a story with tension built in. A constant reminder that Jupiter's system is shaped by drama as much as order. Jupiter's gravity can gradually reshape a moon's orbit over ages. Even when nothing dramatic happens, Jupiter never stops working. Its gravity tugs on moons in subtle ways, and those tiny pulls can add up over very long times. Orbits can slowly shift in distance, tilt, or shape, like a path being gently rewritten without anyone noticing in the moment. The change can come from repeated interactions, from the way moons influence one another, and from the wider gravitational setting of Jupiter moving through the solar system. This means the moon system you see today is not frozen in place. It is a snapshot of a living arrangement that has been adjusting for eons. The past orbits of these moons may have looked different, and their future ones will too. That idea is quietly thrilling because it makes time feel active. Jupiter is not just a planet with companions. It is an engine of slow rearrangement. The system is always becoming something new, just at a pace that only patience can see. Tiny impacts constantly sandblast surfaces, creating fresh dust. Out near Jupiter, the moons are not protected by air or oceans, so even the smallest impacts matter. Tiny grains, moving at high speed, strike like invisible hail, chipping surfaces and breaking rock and ice into finer and finer pieces. Over time, this constant bombardment can soften sharp features, darken bright patches, and create a loose layer of powdery material that covers the ground like a dry snowfall. It is a kind of weathering without weather. The moon is being worked on by space itself. What makes this fascinating is the scale of the slow process. Each impact is small, almost nothing, but the sum of countless hits can transform an entire surface. It can also expose buried material, briefly revealing fresher layers before they too are altered. So a moon's appearance becomes a balance between what it is made of and what space keeps doing to it. The dust is a record of relentless contact, proof that even emptiness can erode a world. That dust can drift into Jupiter's rings like invisible snowfall. Once dust is lifted off a moon's surface, it is no longer just a local coating. It becomes a traveler. Sunlight pressures Jupiter's magnetic environment, and the constant push and pull of gravity can nudge tiny grains into new paths, spreading them outward until they join the faint ring system. It is a delicate kind of motion, because these grains are so small that forces we usually ignore can steer them. The image is mesmerizing. A moon is quietly shedding dust, and the dust becomes part of a planetary feature that encircles Jupiter like a pale veil. It also means the rings are not a single ancient relic. They are continually refreshed by ongoing processes, fed by tiny events happening all the time. This is one of the most beautiful ideas in planetary science, because it turns the system into a loop. Moons create dust. Dust becomes rings. Rings evolve and thin, and then more dust replaces what is lost. Jupiter's rings are not just something you look at. They are something the moons keep making. Moons can raise tides on each other, not just on Jupiter. It is easy to imagine Jupiter pulling on its moons like a puppet master. But the moons tug back, and they tug on one another too. When two sizable moons align in their orbits, their gravity can slightly stretch each other, creating tidal forces that add to the constant bending caused by the planet. These neutral tides are subtle, but they can matter over long periods because they repeat again and again, like a gentle pressure that never fully stops. What makes this captivating is the idea of a moon feeling the presence of another moon in a physical way, not through light or shadow, but through internal stress. It turns Jupiter's system into a network rather than a hierarchy. Worlds are connected by invisible paws shaping each other's interiors without contact. This is also part of why the system can be so dynamic. The moons are not isolated beats on strings. They are interacting bodies, exchanging energy through gravity and slowly changing one another simply by being nearby. Resonance can keep orbits stable for billions of years. Resonance is like a repeated handshake between orbits, where timing locks into a dependable pattern. When moons fall into that pattern, their gravitational nudges happen in a regular way that can prevent chaos from taking over. Instead of drifting into unstable paths, the system can settle into a rhythm that protects it even across unimaginable spans of time. The beauty here is that stability does not arise from stillness. It emerges from motion, repeated with exactness. A resonance can also function like a boundary, guiding where moons can safely remain and where they may be slowly pushed away across long ages. This gives the structure of Jupiter's moon system an almost intentional feel. Even though it is entirely natural, it is gravity finding a way to organize many moving worlds without collisions or dispersal. For a listener, this is one of the deepest ideas of all. It suggests that time itself can act as an engineer. With enough orbits, a system discovers patterns that endure longer than continents, longer than species, longer than memory. Europa's ocean may come into contact with rock, an essential ingredient for chemistry. If water lies directly against a rocky seafloor, it can absorb minerals, dissolve them, and carry them like messages through the darkness. On Earth, some of the most unexpected ecosystems exist where water meets rock in deep places that sunlight never reaches. Europa tempts scientists for the same reason. A seafloor is not just scenery, it is a workshop. Warmth from within can drive slow circulation, and moving water can keep ingredients mixing instead of settling into silence. Even without waves, you could surf. There could be currents, temperature layers, and pockets of concentrated salts and minerals. The thrilling part is how ordinary the recipe sounds, and how extraordinary the setting is. A moon circling a giant planet wrapped in ice may still host the same basic meeting that makes oceans feel alive. Water pressing against stone. Europa's surface likely contains salts carried upward from below. Salt is a storyteller because it does not appear by accident on clean ice. It suggests that something has moved, that material from deeper layers has found a pathway upward, then been left behind when water froze or vapor escaped. Imagine ice that is not pure and blank, but likely seasoned by a hidden ocean, like sea spray on a winter shoreline. Those salts can change how the surface behaves. They can darken patches, alter the way ice melts and refreezes, and leave chemical fingerprints that instruments can read from a flyby. This is why every discolored line on Europa feels important. It could be a trace of exchange between the surface and what lies beneath. Not a wide open doorway, but a slow transfer over time. In a place where you cannot simply drill down, salt is one of the clearest hints that the ocean is not completely cut off from the sky. Chaotic terrain on Europa looks like broken ice refrozen in place. Instead of smooth plains, you see regions that resemble a puzzle dumped onto the floor, with blocks rotated, shifted, and packed together again. This kind of landscape makes you imagine a moment when the shell weakened, cracked apart, and briefly behaved like floating plates. Maybe a pocket of warmer ice rose from below, or a thin region gave way and allowed slushy material to surge upward, then freeze. The result would be a surface that records motion not as a blur, but as preserved fragments, like ice flows caught mid-drift and suddenly locked into stone. That is why chaotic terrain feels so gripping. It is a frozen snapshot of activity, evidence that Europa is not a dead ice ball. Something has pushed, lifted, and rearranged the crust in ways that mimic a sea. Even though everything ends in ice again, some models suggest Europa occasionally vents water into space. The idea is startling because it turns a sealed ocean world into a world that sometimes breathes. If fractures open under stress or pockets of pressurized water and vapor find a weak spot, Europa could release a brief spray above the surface. That would not need to be constant to matter. Even rare outbursts could carry tiny droplets and grains of ice upward, offering a direct sample of the hidden ocean's chemistry. It also reframes Europa's crust as something responsive, flexing and shifting under tides, sometimes cracking just enough to let material escape. For scientists, venting is not just a spectacle, it is an invitation. It suggests the boundary between surface and ocean may not be perfectly sealed forever. For a listener, it makes Europa feel less like a locked vault and more like a world with pressure, movement, and moments of release, all happening in the cold dark near Jupiter. If plumes exist, spacecraft could sample an ocean without drilling. That possibility feels almost magical because it skips the hardest problem, punching through miles of ice. Instead, a probe could fly through a rising cloud and catch particles the way a net catches mist. Those captured grains could reveal what the ocean is made of, which salts are present, whether simple organic molecules are there, and how energetic the environment might be. It changes exploration from a distant survey to something closer to tasting. A single pass could turn Europa from a mystery into a place with measured ingredients. It also shifts the emotional weight of the mission. You are no longer only mapping a frozen shell. You are reaching into a hidden sea with a quick, careful swoop. Even if the plumes are faint or sporadic, the strategy is elegant. It treats Europa as an active world that occasionally offers a sample of itself, and it lets exploration feel immediate rather than impossible. Ganymede's core may be liquid metal generating its magnetic shield. Deep inside, a layer of electrically conductive fluid could be circulating, and moving metal can act like a generator. That is a dramatic thought for a moon because it implies a complex interior with heat, layering, and long-term activity. A core like that would not be visible, but its presence would be announced by the way magnetic forces wrap around the moon. It suggests that Ganymede has an inner engine that never fully shut down, even after billions of years. This kind of core also hints at a past where the moon was warmer, perhaps more restless, with internal processes sorting heavy materials inward and lighter materials outward. The magnetic shield becomes more than protection. It becomes proof that Ganymede is structured like a true world, with deep regions that still behave dynamically. When you imagine liquid metal sloshing beneath an icy exterior, the moon feels suddenly alive in a hidden way. Ganymede's magnetic field carves a tiny magnetosphere inside Jupiter's. Picture a bubble inside a storm, a smaller domain of order nested within a much larger one. Jupiter's magnetosphere is enormous, filled with charged particles and powerful currents. Yet Ganymede can push back enough to create its own pocket where particles are guided differently, where invisible boundaries form and shift. This is rare in the solar system, and it makes Ganymede feel like a world with its own space weather, even when it lives inside Jupiter's bigger weather. That nested structure is fascinating because it is purely electromagnetic geography. Borders drawn without walls. If you could see magnetic lines like glowing threads, you would watch them bend, reconnect, and flow around Ganymede in patterns that change as it orbits. This tiny magnetosphere affects how particles strike the surface and how energy moves near the moon. It is a reminder that space has architecture and that a moon can sculpt it. Callisto sits farther out, spared some of Jupiter's harshest radiation. Distance sounds simple, but in Jupiter's realm, it can mean the difference between constant particle bombardment and a relatively calmer environment. That calmer setting makes Callisto especially interesting as a kind of quiet outpost, a large moon where conditions are less extreme for spacecraft systems and long observations. It also shapes the surface itself. With fewer energetic particles slamming into it compared to inner neighbors, Callisto's outer layers may preserve their character in a different way, aging slowly and keeping signatures that might be erased elsewhere. In the story of exploration, Callisto becomes a strategic place. It is still unmistakably part of Jupiter's world, but it sits near the edge of the worst intensity, like a porch just outside a roaring furnace room. That position adds to Callisto's personality. It is the distant witness, orbiting in relative calm, holding its ancient face steady while Jupiter's inner space rages closer in. Callisto's surface may be a museum of early solar system impacts. When you look at it, you're not just seeing craters. You are seeing a timeline stamped into ice and rock. Many worlds erase their early scars through resurfacing, tectonics, or melting. Callisto appears to have done far less rewriting, so the marks remain layered and crowded like pages left open. Each crater is evidence that the young solar system was messy, filled with wandering debris and violent encounters. Overlapping rings and battered basins show that impacts were not rare events, but a steady rhythm in those early ages. This makes Callisto feel like an archive you can actually visit with cameras and instruments. It holds clues about what kinds of objects were flying around, how often collisions happened, and how surfaces respond when they are repeatedly struck without being renewed. In a sense, Callisto is a memory surface, preserving the solar system's childhood chaos long after other worlds grew out of it. Europa's ice shell might be miles thick, yet still mobile. Thick does not always mean frozen in place, especially when tides keep flexing the shell, and warmth from below keeps parts of it softer than you would expect. Over long spans, ice can behave less like brittle glass and more like a slow-moving material that can creep, bend, and shift. That mobility matters because it turns Europa's surface into something active, capable of rearranging itself without needing wind, rain, or seasons. Cracks can open, edges can shift, and blocks can slowly migrate as stresses build and release. This is why Europa feels so compelling. It looks like a moon that should be silent, yet its skin hints at motion, like a glacier that never stops. A thick shell also suggests protection, a sturdy roof over what lies beneath. So Europa becomes a world with a strong outer armor that still moves, still responds, and still records the pushes and pulls of its orbit. Europa's ocean could contain more water than all Earth's oceans. That single possibility can flip your sense of scale, because Europa looks small in the sky, yet it may hide an enormous reservoir locked away beneath ice. The striking thought is that this water would not sit in open sunlight. It would exist in darkness, wrapped around the moon like a secret layer shaped by tides and pressure instead of weather and coastline. If the estimate is right, it suggests that the solar system's biggest bodies of water might not be on planets at all. They might be buried inside moons. That changes the way you imagine where water lives and what it means for a world to be rich in it. It also makes Europa feel less like an object and more like a place. A deep environment with volume and depth where currents could circulate for ages. Even without seeing it, the sheer potential amount of water is enough to make the moon feel immense. Ganymede is larger than Mercury, yet still a moon. That is one of the most mind-shifting facts in the solar system, because it reveals how misleading labels can be. We call it a moon only because it orbits a planet, not because it is small or simple. A world that big can hold complex layers, a long internal history, and a surface shaped by forces that have nothing to do with being a minor object. It invites a strange thought experiment. If Ganymede orbited the Sun directly, we would probably call it a planet without hesitation. Instead, it circles Jupiter, and that single relationship changes its category, while its physical reality stays the same. This is why Jupiter's system feels like a collection of almost planets, each with enough size to be taken seriously as a world. Ganymede reminds you that Jupiter did not just collect pebbles. It gathered companions that rival full planets in scale, and that makes the whole system feel bigger and more important. Callisto is nearly the size of Mercury, but far icier. Two worlds can be similar in size and still feel like they belong to completely different universes. Mercury is built for heat and sunlight, while Callisto lives in the cold outer realm, where ice becomes a major building material, and rock can be mixed with frozen compounds. That difference changes how the surface responds to impacts, how heat moves inside, and how the crust develops over time. It also changes the texture of the world you would stand on. Callisto's ground would not be a sun-baked plain. It would be a frozen landscape that carries scars in the material that behaves differently than hard rock alone. This contrast is fascinating because it shows that size does not determine personality. Environment does. By comparing Callisto to Mercury, you start to see Jupiter's moons as real planetary rivals, worlds that could stand beside planets in importance, yet built from a colder recipe. Callisto is a reminder that the solar system can produce twin-sized bodies with completely different identities. The Galilean moons likely formed in a temperature gradient around Jupiter. Picture a young Jupiter surrounded by swirling material, warmer close in and colder farther out, like a gentle heat map in space. In that setting, what could condense and stick together depended on location. Closer regions favored sturdier, less volatile ingredients, while farther regions allowed more frozen materials to join the building process. That kind of gradient is compelling because it makes the system feel organized from the start, as if the moons were shaped by invisible climate zones around a planet. It also helps explain why these 4 major moons feel like a sequence rather than random peaks. Each one reflects a different balance of materials and history, as if they grew up at different distances in the same nursery. The idea turns Jupiter into a miniature solar system maker with its own internal pattern of warmth and cold, guiding what kinds of worlds could take shape. When you imagine that early disk, you can almost see the moons forming in place, each gathering what its region offered. Inner moons formed rockier, outer moons formed icier. This is a simple pattern with enormous meaning because it shows how distance from a heat source can quietly decide what a world is made of. In a warmer zone, ices struggle to survive, so rock becomes the backbone. In a colder zone, frozen materials can accumulate, adding bulk and changing how a moon behaves over time. That difference influences everything from density to surface style, from how craters look to how the interior stores heat. It also means the moons of Jupiter are not just a list of names. They are a gradient of environments, like stepping stones across a changing temperature landscape. When you travel outward in your imagination, you are also traveling through a shift in ingredients, from tougher, heavier materials toward worlds with more frozen content. The wonder is that you can read that ancient temperature pattern today, still written into the moons themselves. Jupiter's system becomes a lesson in how place can shape destiny, not through spectacle, but through quiet physics. Jupiter's enormous gravity has captured many wanderers across cosmic time. Imagine the early solar system as a crowded arena filled with objects crossing paths, and Jupiter as a massive presence capable of turning a passing traveler into a lasting companion. Capture is not like adoption with formal steps. It is more like a close encounter that drains momentum, leaving an object without the energy needed to escape. Over vast stretches of time, this process can assemble a collection of moons with many different origins, some formed close to Jupiter, others arriving from far away. That diversity is part of what makes the system so compelling. Each captured moon becomes a souvenir from a different region, a fragment of wandering history preserved in orbit. It also shows that Jupiter has shaped the solar system not just by being there, but by actively collecting and rearranging whatever passed nearby. When you observe Jupiter's outer moons, you are seeing the long outcome of countless encounters. The planet becomes a kind of gravitational museum, quietly holding on to travelers that might otherwise have remained anonymous. Some captured moons may be related to asteroids, others to distant icy bodies. Jupiter's outer moon collection is like a mixed box of souvenirs from different neighborhoods of the solar system. Some of these moons resemble asteroids in their darkness and density, suggesting they may have once wandered among rocky populations before drifting too close to Jupiter. Others look more like cold, carbonary objects that formed farther out where ices and complex materials were easier to preserve. That variety matters because it turns Jupiter into a sampler of ancient regions we cannot easily visit in bulk. Each captured moon is a small clue about what was moving through the early solar system, what kinds of objects were common, and how far they traveled. It also means two moons can share the same planet, yet have completely different birthplaces. When you imagine their first encounters with Jupiter, you can almost feel the moment a traveler becomes a permanent companion, carrying the chemistry of its origin into a new orbit. The outer moon's tilted orbits suggest violent beginnings. Tilted orbits are like crooked rings around Jupiter, and they usually do not come from calm formation. Many of these moons circle at steep angles compared with Jupiter's equator, as if they arrived from random directions and never fully settled into the planet's main orbital plane. That tilt hints at a rough history of close passes, gravitational wrestling, and chaotic traffic when the solar system was younger. It is the kind of signature you would expect after a dramatic capture or a major disruption where an object's path was bent into a new shape, rather than gently built in place. Over time, these tilted orbits can remain as stubborn evidence even after everything else has aged. They make Jupiter's outer region feel like a frontier, with scars you can measure. Instead of neat circular lanes, you find slanted, eccentric paths that tell you Jupiter's moon system includes survivors of upheaval, not only products of peaceful assembly. Collisions among irregular moons can create entire new moon groups. In the far reaches around Jupiter, small moons can meet in catastrophic ways. Their speeds are high, their shapes are uneven, and their orbits can cross at angles that make impacts more likely than you might expect in open space. When two irregular moons collide, they do not merge into a bigger moon. They often shatter, producing many fragments that spread out but still share a family resemblance in their orbital traits. Over long periods, those fragments can become a recognizable group, a cluster of moons with related paths that point back to a single destructive event. This is fascinating because it means moon populations can grow through breakage, not birth. A collision can manufacture a whole new set of names on the chart. And the aftermath can persist for ages. Jupiter's system then becomes a living record of impacts, where creation sometimes arrives wearing the mask of destruction. Each moon group is like a fossil record of a single catastrophe. When astronomers identify a moon group, they are often seeing the long shadow of one specific moment. The shared orbital patterns act like matching fingerprints, implying these moons were once part of a single body that was torn apart by an impact. That makes a group feel like a fossil bed, except the fossils are still moving. The catastrophe itself is gone, but its structure remains, preserved in the way the fragments circle Jupiter together. From those patterns, scientists can infer how the breakup happened, how forceful it was, and how widely the fragments should have spread. It is detective work on a cosmic timescale, built from motion rather than bones. The eerie beauty is that the evidence never stops repeating. Every orbit replays the result of that ancient collision. Even a tiny moon becomes a witness, and a whole group becomes a preserved snapshot of violence that happened so long ago it feels almost mythic. Yet it is still legible today. Jupiter's moons interact with plasma, creating invisible electrical circuits. Near Jupiter, space behaves less like emptiness and more like a charged ocean. Fast-moving particles fill the region, and when a moon travels through that environment, it can disturb and channel those particles in surprising ways. The motion sets up electrical currents that connect the moon to its surroundings, forming pathways that are real, measurable, and completely invisible to the eye. It is as if the moon is dragging an electrical wake behind it, like a boat pulling ripples through water. These interactions can influence how particles hit the surface, how the nearby space glows at certain wavelengths, and how energy is transferred through Jupiter's environment. The wild part is that this circuitry is not built by technology. It is built by motion, magnetism, and charged particles. Simply because a moon exists and keeps orbiting, Jupiter's system becomes not only a set of rocks and ice, but a working electrical machine, quietly running without switches or wires. Io's orbit helps feed a giant ring of charged particles. It moves through Jupiter's intense magnetic environment like a match dragged across a rough surface. Material released from Io does not always stay neutral. it can become electrically charged and swept up into Jupiter's rotating magnetic system, spreading outward into a vast region of energized particles. This creates a huge structure that is more like a circulating cloud than a solid ring, and it is powered by the combination of Io's supply and Jupiter's magnetic force. The result is an environment that can glow in certain ways and behave like a dynamic belt of charged matter. It is a stunning example of how one moon can influence an entire planetary system far beyond its physical size. Io is not just being affected by Jupiter. It is actively contributing to Jupiter's space environment, helping build a feature that exists on a scale that dwarfs the moon itself. Orbit becomes production, and motion becomes a kind of invisible manufacturing line. That material forms a vast torus around Jupiter like a hidden halo. Picture a donut-shaped region encircling Jupiter, not made of rock or ice, but of charged particles moving in a broad band. This structure is immense, wrapping around the planet in a way that is more like a glowing presence than a ring you can easily photograph. It is called a torus because of its shape, and it exists because particles supplied from the inner system get trapped and guided by Jupiter's magnetic field. The torus matters because it turns the area around Jupiter into an environment with its own behavior. Almost like a weather system in space, it can brighten, thin, shift, and respond to changes in supply and magnetic conditions. For storytelling, it is mesmerizing, because it is a planetary feature you could never see with your eyes alone. Yet, it is real and influential. Jupiter is surrounded by an unseen halo of moving charge, and some of its moons help keep that halo stocked. Europa's surface chemistry may be altered by energetic particles from Jupiter. Europa sits in a harsh particle environment, and that bombardments can act like a chemical workshop on the surface. Energetic particles strike the ice and can break molecules apart, allowing new substances to form that would not appear in a calm, sheltered setting. This means Europa's surface is not just old ice. It is ice that has been processed, changed, and rewritten by Jupiter's environment. The fascinating twist is that chemistry here is driven from above rather than below. Space itself becomes the active ingredient, constantly modifying the topmost layer. Those changes can affect color, texture, and how the surface reflects light, leaving subtle clues that spacecraft can detect. It also raises an irresistible possibility. If surface material is chemically altered, and if any exchange processes exist, then products made on the surface could eventually be transported downward. Europa becomes a two-way story, with Jupiter's particles shaping the surface while the hidden ocean waits beneath, potentially receiving whatever the surface slowly prepares. Radiation can spit water molecules, creating reactive compounds on the ice. When energetic particles strike water ice, they can break it into fragments that do not want to stay calm. The pieces can recombine into substances that are more chemically reactive than plain water, creating a thin skin of altered material on the surface. This is compelling because it suggests Europa's icy exterior is not chemically quiet, even in deep cold. It is being energized by an external power source, turning simple ice into a place where new compounds can form. Think of it as a slow, constant chemistry experiment running across an entire moon, powered by Jupiter's surrounding radiation. The products can build up, change the surface's character, and create pockets of material that differ from pristine ice. This matters for exploration, because it means a surface sample is not just a sample of frozen water. It is a sample of a process, a record of reactions driven by space. Europa's ice becomes an active interface where energy arrives, molecules break, and new chemistry quietly begins. Those compounds might drift downward, delivering energy to an ocean. If surface-made compounds can migrate into fractures or slowly mix into deeper layers, they could act like packaged energy, traveling from the surface to the hidden sea. On Earth, chemical energy can fuel ecosystems even without sunlight, and Europa tends the imagination with a similar possibility. The surface could be manufacturing reactive materials, and the interior could be receiving them in small doses over long times that would connect two worlds: the harsh radiation-processed exterior and the dark ocean below through a slow delivery system. It is not a dramatic waterfall of chemistry. It is more like a steady trickle, the kind of quiet supply line that matters most over ages. The beauty of the idea is its simplicity. Jupiter provides the energy that drives reactions at the surface, and Europa's own structure might provide pathways for the products to move downward. A moon becomes a chemical bridge between space and sea, with energy changing hands in the dark. Ganymede's surface shows grooved terrain, as if the crust stretched open. Long bands and ridges run across wide areas, giving the moon a look that feels worked, not merely cratered. It is as though the outer shell was pulled apart, then partly healed, leaving parallel textures like fingerprints pressed into ice and rock. These grooves are exciting because they hint at a time when Ganymede's skin was not quiet. Something supplied stress and motion strong enough to reshape an entire hemisphere, not in one violent blast, but through repeated planet-sized strain. The grooves also divide the moon into distinct terrains, making it feel like a world with chapters, where one era left ancient scars and another later era overwrote parts of the page. When you picture standing there, the landscape would not look random. It would look organized, as if the crust once slid, stretched, and locked again, preserving the memory of a restless interior. That grooving hints at tectonic activity on an icy world. Tectonics usually makes people think of Earth, of plates grinding and mountains rising. But Ganymede offers a colder version of the same idea, where ice can behave like rock if the pressures and temperatures are right. The most gripping part is that this is not surface decoration. It suggests the crust was capable of moving, cracking, and reorganizing, which means the moon once had enough internal energy to keep its outer shell from becoming a permanent statue. Some regions appear to have been resurfaced, as if newer materials spread into older terrain and smoothed it, before later fracturing again. That is a story with momentum, a world that went through phases rather than remaining unchanged. It also makes icy moons feel less like frozen leftovers and more like dynamic bodies with geology of their own. Ganymede shows that tectonics is not a uniquely warm planet privilege. Under the right conditions, even ice can take on the role of moving crust. Callisto lacks strong tectonics, preserving its ancient scars. Instead of seeing a moon that has been frequently remodeled from within, you see a surface that has mostly kept what happened to it, like an old book that was never revised. That quiet matters because it makes Callisto a reference point. When you compare a busy world to a calm one, you can start to separate what came from impacts and what came from internal activity. On Callisto, the lack of major reshaping means craters, basins, and bright rings can remain legible for extremely long spans of time. It gives the moon a solemn beauty, as if it has been watching the solar system's history rather than participating in constant reinvention. There is also a strange comfort in that stillness. A moon can be scientifically thrilling precisely because it did not do much. Because it stayed cold enough, rigid enough, and quiet enough to keep its early record intact. Callisto is like a memory you can fly past, and the memory holds. Europa's cracks often run for hundreds of miles across the globe. They are not short fractures you could step over. They are sweeping lines that cut across continents worth of ice, suggesting forces that act at planetary scale. What makes them so captivating is their elegance. Many of these features curve and intersect like an enormous network, hinting that Europa's shell is repeatedly stressed, opened, shifted, and then sealed again. In some places, the cracks appear as paired ridges, as if material welled up along the edges and froze, building low walls that trace the original split. In other places, the lines look darker, as though they have been dusted with foreign material or altered by surface chemistry. Each crack feels like a message written by gravity because the pattern is too widespread to be a local accident. Europa's surface becomes a kind of map of tension, showing where the ice has been pulled and persuaded into motion. You are looking at a frozen world that still behaves like it is alive under its own skin. The moon's day lengths match their orbits because they are tidally locked. This means the same side of each moon continually faces Jupiter, like a person who cannot stop looking at a giant presence in the room. The impact is striking. One hemisphere becomes the side that always faces Jupiter, forever receiving that view, while the opposite side never sees the planet at all. Over time, this unchanging orientation can influence a moon's experience, from how it heats and cools to how material settles and where stresses build up. It also sets up a kind of dependable rhythm for storytelling. As the moon moves around Jupiter, sunrise and sunset follow a schedule linked directly to its orbit, not to an independent spin. If you lived there, you could keep track of time by Jupiter's position in the sky, never needing a compass. Tidal locking is a reminder that gravity does more than keep you in place. It can also determine how you rotate, how you face, and what you witness again and again forever. That locking ensures each moon always presents the same face to Jupiter. It forms a lasting bond between two bodies, like a slow dance in which one partner never turns away. The near side becomes a familiar stage, and the far side becomes a private world. This can make the moons feel strangely personal, as if they have a public face and a hidden back. It also means Jupiter would hang in roughly the same place in the sky on the near side, not wandering like the moon does from a single spot on Earth. For anyone imagining a landscape, the sky itself gains a fixed landmark that never leaves. That constant presence could influence how people would navigate, where they would build, and even what they would feel. The far side, by contrast, would have a sky without Jupiter at all, only stars and sunlight and darkness. That contrast is one of the most haunting ideas in planetary motion. A single gravitational rule can divide a world into two experiences that never swap. From Europa, Jupiter would loom enormous, striped, and terrifyingly close. It would not be a distant ornament. It would dominate the sky like a vast ceiling with bands, storms, and shifting colors that change over hours. You could watch cloud features slide along the face of a planet so large it feels unreal, and you would sense its pull in the ground beneath you, because Europa's tides are driven by that nearby mass. The emotional effect is easy to imagine. The planet would feel like a guardian, and a threat at the same time. Beautiful, immense, and unavoidable, its changing brightness would also shape the night, casting a faint glow when Jupiter is up and leaving deeper darkness when it is not. The sky would have a main character, and because Europa is tidally locked, that main character would keep returning to nearly the same place, making Jupiter a constant companion for anyone standing on the near side. Europa would feel less like a moon in space and more like a world living in the shadow of a giant. From Io, Jupiter's glow would dominate the sky like a giant lantern. Io orbits closer, so Jupiter would appear even larger and brighter, filling the heavens with reflected sunlight and pale color. The night would not feel fully dark when Jupiter is above the horizon, because its light would spill across the landscape in a steady wash. That glow would not be calm in the way moonlight on Earth can be calm, because Jupiter's face is active and its patterns shift. You could watch bright zones and darker belts slide, and you might even notice the silhouettes of other moons crossing in front of the planet as moving dots. The sense of proximity would be constant. Io would feel like it lives inside Jupiter's presence, with the planet occupying a huge portion of the sky and reminding you visually that this moon is held close by a powerful neighbor. It is a strangely intimate setup, a volcanic world under an enormous glowing planet where the sky itself feels heavy with the idea of gravity. The Galilean moons eclipse one another, casting fast-moving shadows. Because these moons share a plane and circle quickly compared to outer moons, alignments happen with surprising regularity. When one passes into another's shadow, the lighting can change abruptly, like a cosmic curtain dropping on Jupiter itself. You can also see their shadows race across the cloud tops as small dark spots, a visual reminder that these are solid worlds crossing between sunlight and the planet. The speed is what makes it thrilling. These are not slow, once-a-lifetime events. They are part of the ongoing clockwork of the system, and they reveal the geometry of the orbits in a way your intuition can grasp. Shadow becomes measurement. Alignment becomes proof. Even with modest equipment, careful observers can watch the dance and see the system rearrange itself across a single evening. It is a living demonstration of orbital mechanics written in light and darkness, happening far away, yet visible from home. Those eclipses helped astronomers refine ideas about the speed of light. The key insight came from timing. When a moon's eclipse should have happened at a predictable moment, observers noticed the timing could appear early or late depending on how far Earth was from Jupiter in its own orbit. The simplest explanation was bold for its time. Light does not arrive instantly. It takes time to cross space. So the same event could be seen sooner when Earth was closer and later when Earth was farther away. Not because the moons changed their behavior, but because the message traveled at a finite speed. That is an astonishing use of distant worlds. Jupiter's moon system became a natural laboratory, offering repeating events reliable enough to test a deep property of the universe. It also shows how everyday observation can become profound. By watching a tiny dot disappear and reappear beside Jupiter, people uncovered a truth about how reality transmits information. These eclipses turned a distant dance into a ruler for one of nature's most important limits. Galileo's discovery of Jupiter's moons reshaped humanity's place in the cosmos. With a small telescope, he watched tiny lights change position night after night, always staying near Jupiter, always returning, always behaving like companions in orbit. That simple motion did something explosive to the imagination. It suggested the universe could have more than one center of turning, more than one system of bodies circling something larger. the sky stopped being a fixed decoration and became a place with layered structure. It also meant that careful observation could overturn ancient certainty, not with philosophy, but with repeated, checkable patterns anyone could follow. In a quiet way, Jupiter became a teacher. It offered a visible example that the heavens were not arranged solely around us. Those drifting points of light opened the door to a bigger idea, that Earth is one world among many in a cosmos full of other arrangements, other rules, and other centers of gravity. Seeing moons orbit Jupiter proved not everything circles Earth. It is hard to overstate how strange that would have felt at the time, because it provided a working counterexample you could point to in the sky. If small bodies could circle Jupiter, then Earth was not the only possible hub for motion. The idea of a single, universal center started to loosen. Suddenly, you could imagine nested systems, with moons around planets and planets around the sun, and perhaps other suns with their own companions. The power of the observation is how direct it is. You do not need complicated theory to grasp it. You watch the dots change place. You track their rhythm, and you realize you are witnessing a miniature system that does not include Earth at its center. That realization is both humbling and thrilling. It turns the night sky into a space of multiple neighborhoods, not one grand stage built only for us. Europa and Ganymede are top targets in the search for habitable oceans. Not because anyone expects a sunny paradise, but because both moons hint at hidden water environments that could persist for very long spans of time. Habitability in the scientific sense is about stable ingredients and steady energy, and these moons may offer both in different ways. Europa is compelling for its active, stressed exterior and the possibility of exchanges between the surface and what lies beneath. Ganymede is compelling for its size, its deep interior complexity, and the way it behaves like a full world rather than a simple satellite. The excitement comes from the question itself. If oceans can exist under ice here, then they can exist in many places, and life would no longer feel tied to warm, sunlit surfaces. These moons invite a new kind of hope, one that is quiet and patient, focused on chemistry, time, and hidden water. Future missions plan close flybys to map ice, heat, and chemistry. The strategy is careful and surprisingly intimate. Instead of one distant glance, a spacecraft can skim past again and again, building a detailed portrait from repeated encounters. Instruments can look for warmer regions that hint at internal energy, scan the surface for signs of unusual composition, and measure subtle changes that reveal what is happening beneath the visible shell. Each flyby is like reading another page of a book you cannot open all at once. You gather clues from texture, from temperature, from magnetic signatures, and from the way the surface reflects light. Over time, patterns emerge, and the moons stop being mysterious circles and start becoming places with regions, histories, and active processes. The beauty of flybys is that they turn exploration into listening rather than drilling. You do not have to break the ice to learn from it. You pass close, you measure carefully, and you let the moon tell its story through data. Europa's surface may be young because old ice gets recycled. On many worlds, age is written in craters, with older surfaces showing more scars. Europa appears different, suggesting that parts of its exterior have been renewed. The idea is that the ice shell is not a single frozen slab that lasts forever. It may slowly move, break, and replace itself, burying older terrain and revealing newer material in its place. That kind of recycling is captivating because it implies a moon that refreshes its own face without winds, rain, or oceans exposed to sunlight. It is a world that may erase its past the way a slow-moving glacier can cover a landscape, except on a planetary scale. If the surface is being renewed, it also means Europa could be active in the present, not only in the distant past. A younger look exterior becomes a hint of ongoing motion, a subtle sign that something beneath the ice is still influencing what we see from space. Some Europa regions look like ice rafts that drifted and refrow. The patterns can resemble plates of crust that broke apart, shifted position, and then locked back into place, like sea ice rearranging after a storm. That image is powerful because it turns Europa from a static, frozen sphere into something that behaves at times like a surface with mobility. If rafts really moved, then the shell must have been weakened or partially separated by warmer, softer material below, allowing blocks to slide before everything stiffened again. It is the kind of process that would leave behind jumbled edges, mismatched seams, and regions that look stitched together rather than grown smoothly. These landscapes invite a question you can feel in your bones. What moved them? How often does it happen? Where does the displaced ice go? Even the possibility of raft-like motion makes Europa feel dynamic, like a moon with a restless skin that occasionally breaks its own rules, shifts, and then freezes into a new arrangement. Io's constant eruptions mean its surface has few long-lasting craters. Impacts still happen, but the evidence does not get to linger the way it does on quieter worlds. Fresh deposits can spread across the ground, covering older scars and flattening small features until they fade into the background. That makes Io a strange kind of timepiece. Instead of preserving ancient history on its face, it keeps resetting the clock. The landscape becomes a record of recent activity, not a museum of early impacts. This is fascinating because it flips what we often expect from a moon. You might assume a small body is a static relic, but Io behaves like a world that refuses to settle down. Its surface is more like a stage between scenes, constantly being swept and repainted. For a storyteller, that means every view of Io is a moment, a snapshot of an ongoing process, with the understanding that the same place could look different again in the future. Ganymede's magnetic field can shield parts of its surface environment. A magnetic field guides charged particles, bending their paths and shaping where they can easily strike. That means some regions of Ganymede may experience a different particle weather than others, not because of mountains or air, but because of invisible lines of force. It is a haunting concept. The space above the surface is not uniform. It is structured with corridors and boundaries created by magnetism alone over a long time that can influence surface chemistry and the way materials are altered, creating subtle differences from place to place. It also gives Ganymede a planetary quality, because this kind of shielding is something we associate with larger worlds that have active interiors. Here it is happening on a moon, a body that can carve out protective behavior inside a much larger magnetic environment. It is a reminder that protection in space does not always come from thickness or distance. Sometimes it comes from a hidden engine turning deep inside. Callisto's distant orbit makes it a potential stepping stone for exploration. In the Jupiter system, location is everything, and being farther out can mean a comparatively calmer operational environment for spacecraft. Callisto is still close enough to Jupiter to be part of the story, yet distant enough to offer a more manageable place to linger, observe, and plan. That makes it appealing as a staging area. a place where missions could practice longer operations and gather data while avoiding some of the more punishing conditions closer in. It also offers a sense of stability in a system full of extremes. If humans ever build a deeper presence in the outer solar system, they will need places that balance scientific value with practicality. And Callisto often enters that conversation. The romance of it is easy to feel. A quiet, ancient moon, circling at the edge of Jupiter's busiest regions, could become the porch light for journeys deeper into the giant planet's world of moons. Small inner moons can be shaped by Jupiter's tides into elongated forms. Close to a giant planet, gravity does not pull evenly. The near side feels a stronger tug than the far side, and over time, that difference can subtly stretch a small moon. If the body is weakly held together, perhaps porous or fractured, it can be sculpted into a more oval shape, like a piece of soft material, slowly pulled into a new outline. This is compelling because it makes tides feel real and touchable. We usually imagine tides as water shifting along a shoreline, but here tides become sculptors of solid worlds. The shaping is slow and patient, unfolding across immense spans of time, turning a moon's very outline into evidence of where it resides. An elongated inner moon is like a visible stress signature, proof that Jupiter's gravity is more than an anchor. It is a force capable of reaching into a moon's interior and gradually reshaping its body. Amalthea's orbit lies within intense radiation, placing it in a hazardous neighborhood. Close to Jupiter, space is crowded with fast-moving particles that can damage electronics and steadily transform exposed surfaces. For a spacecraft, this means shielding matters, timing matters, and each passage through the region becomes a test of endurance. For Amalthea itself, it means its surface is constantly being processed, as if the environment were sanding and chemically altering the moon from the outside inward. The idea is unsettling in the best way. A small, fragile-looking moon is surviving in a place that behaves like an invisible storm. You can imagine Jupiter as a giant engine accelerating particles and sweeping them around, while Amla keeps orbiting through it again and again for ages. This neighborhood also helps explain why the innermost region of the system feels so extreme. It is not only gravity that makes Jupiter powerful. It is the energetic space it creates, turning nearby orbits into harsh, high-stakes territory. Some tiny moons may have been born from ring material clumping together. That is a wonderfully strange origin story because it flips the usual picture. Instead of moons creating rings, rings could sometimes create moons, gathering dust and fragments into a small body that finally becomes big enough to hold itself together. It would be like watching a cloud slowly learn how to be a pebble. In Jupiter's rings, collisions are constant, and some pieces can stick briefly, forming little piles that survive long enough to grow. Not every clump would last. Many would be torn apart by tides or broken by fresh impacts. But the possibility alone makes the ring region feel alive with experiments. If ring-worn moons exist, they are proof that the system can recycle its own debris into new objects, even if they are tiny and temporary by cosmic standards. The romance is that a moon could begin as drifting dust, then slowly earn a name by staying whole. It is creation happening in plain orbit. Jupiter's rings are faint, partly because moon-fed dust is constantly lost. Dust grains are light enough that they do not behave like solid boulders. Sunlight can nudge them. Jupiter's environment can charge them. And tiny collisions can kick them onto new paths. So even if moons keep supplying fresh material, the rings struggle to hold on to it for long. That makes the rings feel like a balancing act rather than a permanent monument. They exist because replacement keeps arriving even while disappearance never stops. Imagine trying to draw a circle with powder in a wind tunnel. You can do it, but only if you keep adding more powder. Jupiter's rings are like that, maintained by countless small events that happen quietly, day after day, impact after impact. The faintness becomes meaningful. It is a sign of constant motion and constant loss, telling you the rings are not ancient jewelry sitting untouched. They are a living haze, always being rebuilt and always trying to fade. Irregular moons can have retrograde orbits that resist neat prediction. When a moon travels backward and far out, its path is more vulnerable to subtle tugs from other bodies and long-term gravitational nudges. Over time, those influences can make an orbit drift in ways that feel stubbornly complicated, especially compared with the clean, steady lanes of the major moons. This is not chaos like a coin toss. It is complexity like a slow, shifting dance in a crowded room. The moon still follows gravity, but gravity has many hands in play. That unpredictability is part of the fascination because it turns these tiny moons into dynamic objects that require constant attention to understand. Their futures are not simple repeats. Their paths can gradually change, and that can reshape how they interact with the rest of Jupiter's distant population. For a storyteller, they are like wild satellites on the edge of the system, keeping their odd backward motion while the universe keeps gently pushing at the details. They prove that orbiting is not always tidy. Sometimes it is a long negotiation. Their paths reveal Jupiter's history as a gravitational collector. The distant moons act like receipts from ancient encounters, because their strange tilts and far-flung distances suggest they were not made quietly in the same place. Each unusual orbit hints at an object that wandered in, passed close, and ended up trapped in Jupiter's influence. That makes the moon system feel like a gallery of arrivals. Some visitors may have come from rocky regions, others from colder reservoirs, and their present-day routes preserve that mixed heritage. The most captivating part is that the evidence is written in motion. You do not have to dig into the ground to find the story. You track the orbit and the story starts to appear. Jupiter's collection also implies the early solar system was crowded with many opportunities for close calls. In that era, Jupiter was not just a planet. It was a powerful participant, changing the fates of passing bodies by keeping them. Today, those captured objects keep circling like old trophies, except the trophies are worlds. Some moons orbit so far out they are barely bound to Jupiter. At those extreme distances, Jupiter's grip is real but not absolute. The moons move slowly, spending long stretches in the outskirts where the planet feels more like a distant anchor than an overwhelming presence. It is a haunting way to orbit, because the boundary between belonging and drifting away becomes thin. These moons sit in a region where outside influences matter more, where a gentle tug can slowly reshape the future, and where the idea of escape is not fantasy. It is a long-term possibility. Their existence also changes how you picture Jupiter's realm. The planet does not only have close companions, it reaches far, holding objects in a vast volume of space, as if its neighborhood extends far beyond what a casual glance would suggest. When you imagine standing on one of these far moons, Jupiter would look smaller, but its importance would feel deeper. It would be the reason you are still in orbit at all. At those distances, the Sun's gravity tugs hard on their motion. Far from Jupiter, a moon is not only responding to the planet, it is also responding to the star that rules the entire solar system. The result is a delicate competition of pulls, where Jupiter tries to keep its companion, while the Sun quietly leans on the orbit from the outside. This creates a feeling of tension built into the sky itself. A far moon's path can be slowly adjusted by solar influence, like a thread being pulled sideways while it still loops its anchor. That means the most distant moons are not just distant in space, they are distant in loyalty, living in a region where Jupiter's control has to be continually maintained by gravity rather than taken for granted. It is a wonderful reminder that orbits are not private affairs. Even when a moon belongs to a planet, the star still participates. The Sun is always present, even in Jupiter's shadow, shaping motion through steady, patient force. The boundary where Jupiter dominates is called its hill sphere. It is not a hard wall you could bump into, but a region where Jupiter's gravity becomes the main authority over what can remain a long-term companion. Inside that zone, moons can orbit in relative security. Near the edge, stability becomes more delicate, and the wider solar system begins to pull harder on the story. Thinking about this boundary is powerful because it turns gravity into geography. It gives Jupiter an invisible territory, a kingdom defined not by clouds or rings, but by the reach of attraction. It also explains why the most distant moons feel so precarious. They live near the borderlands, where a small change over a long time can matter. The hill sphere concept helps you picture how giant planets act as local centers, each with a sphere of influence that competes with the Sun's pole. When you imagine Jupiter traveling around the Sun with this invisible region moving with it, it feels like watching a planet carry its own moving domain through space, holding moons inside like floating citizens. Jupiter's moon system is like a miniature solar system around a planet. There are inner regions, crowded and fast, outer regions, sparse and slow, and a mix of worlds that formed locally alongside bodies that arrived later as captured visitors. That variety creates the same kind of layered complexity we associate with the Sun's realm, but scaled down and tightened around one giant planet. It is mesmerizing because it means you can study big solar system themes in one place. Formation, capture, collisions, and long-term stability all play out in Jupiter's neighborhood like a condensed version of the broader cosmic story. It also changes what Jupiter feels like. It is not only a planet you visit, it is a central object with its own population of companions, each orbiting as part of an intricate arrangement. When you think of it this way, you stop imagining Jupiter as a single destination and start imagining it as a system you could explore for years without ever running out of worlds. Each moon is a stop, but the choreography between them is the real marvel. Each moon tells a different story of fire, ice, capture, and time. Some worlds are built around internal heat and constant change, while others hold on to ancient scars like a careful archivist. Some likely arrived as strangers, dragged into orbit by a close encounter, while others grew up in Jupiter's own early disk and never knew another home. That diversity matters because it means Jupiter's system is not one tale repeated. It is a library with different genres living side by side. You can move from a moon shaped by ongoing power to a moon shaped by patience, from a companion that behaves like a planet to a tiny, irregular object but still refuses to be forgotten. And because these moons share the same dominant planet, they also share a stage, making their differences even sharper. Jupiter becomes a curator of contrasts. When you listen to the moons as separate characters, the system stops being a list of names and becomes a set of lives, each revealing a different way a world can exist, evolve, and endure. Io's tidal heating is powered by Jupiter and neighboring moons together. Io is squeezed by Jupiter's gravity, but the real trick is that it never gets a perfect rest. Nearby moons keep tugging Io's orbit slightly out of round, so the squeeze changes from moment to moment instead of settling into a steady, boring circle. That changing pull flexes Io's interior over and over, like bending a thick wire until it warms. The heat does not come from sunlight, and it does not require a giant internal furnace left over from formation. It is generated by motion that refuses to calm down. This makes Io one of the clearest examples of a world powered by relationships. Its geology is not only about what Io is, but about who Io orbits with. Remove the neighbors, and the story changes. Keep them, and you get a moon that turns gravity into heat, and heat into constant activity. All because the system keeps time imperfectly. Without resonance, Io would cool and quiet down. Resonance is the reason Io cannot relax into a simple circular orbit. If that special timing relationship disappeared, Io's path would gradually become more even, and the repeated flexing that generates internal heat would fade. The moon would start to lose its most defining energy source, not in a dramatic instant, but through a long dimming. Volcanic output would shrink. The surface would stop being refreshed so often, and the landscape would begin to keep its scars instead of constantly covering them. Over immense time, Io would become more like an ordinary moon, a place where the past stays visible because the present is no longer rewriting it. This is a powerful thought because it shows how fragile a world's personality can be. A moon can be extreme not because it is destined to be extreme, but because it is held in a particular rhythm by its neighbors. Change the rhythm, and you change the moon. Io teaches that geology can depend on orbital music, and silence can arrive when the beat stops. Europa's tides flex its ice, potentially keeping the ocean from freezing solid. Europa lives in a perpetual push and release. As it travels around Jupiter, the pole varies enough to flex the ice shell, and that flexing can create heat within the crust itself. The warmth does not need to be fiery. A small, steady input is enough to matter when you are trying to keep water from locking into a permanent, planet-wide block of ice. This is why Europa feels like a world balanced on a knife edge. Not warm, not dead cold, but maintained in an active middle state by repeated motion. The flexing also means the shell is under stress, which can encourage cracking, shifting, and gradual reshaping. Europa for exploration. That is thrilling because it implies a living interface between the surface and the hidden sea. A lid that is not simply sitting there. Europa becomes a moon where gravity supplies maintenance heat, like a quiet engine that keeps the ocean from becoming a fossil. The ocean, if it persists, is not a miracle. It is an outcome of constant bending. Ganymede's lay interior suggests a long history of internal sorting. Inside a large world, heavy materials tend to sink, and lighter materials tend to rise. But this sorting requires time and enough warmth for things to move. Ganymede's interior structure points to a long, patient process where layers separated and organized, creating a world with depth and complexity, rather than a simple mixed ball. That history is fascinating because it implies stages. Early on, the moon may have been warmer, allowing materials to rearrange. Later, it cooled into a layered state that still preserves that internal architecture. Layering also means Ganymede's present-day behavior is shaped by what is hidden, not just what is visible. The way heat travels, the way pressure builds, and the way any subsurface liquids persist would all depend on how those layers stack and interact. It turns Ganymede into a world with an internal biography. You are not only looking at a surface, you are looking at the outcome of long-ago decisions made by gravity and temperature, slowly organizing a moon from the inside out. Callisto's mixed interior hints it never fully melted and separated. Callisto appears to have avoided a complete internal makeover. Instead of melting deeply enough for heavy material to sink cleanly into a distinct core and for lighter material to rise into neat layers, its interior seems more blended. That is an arresting contrast with more differentiated worlds, because it suggests Callisto stayed cooler during key early periods when other bodies were sorting themselves out. The consequence is that Callisto may preserve a more original mixture of ingredients, closer to what was assembled in the early outer solar system. It also means the moon's evolution was quieter, with fewer chances for internal heat to drive widespread restructuring. This kind of incomplete separation makes Callisto feel like a time capsule, in a different sense than crater records. The history is not only written on the surface, it is retained inside the body itself, in the way materials remain mixed. Callisto becomes a reminder that two worlds can end up similar in size, yet radically different in internal life. Sometimes the most revealing story is the one that never fully happened. Some Jovian moons may be comet fragments, trapped long ago. Not every moon around Jupiter is necessarily native to the Jupiter neighborhood. Some small distant companions may be leftovers from icy visitors that once traveled on long solar orbits, closer in spirit to comets than to locally formed satellites. If an icy body passed Jupiter at just the wrong angle and speed, gravity could steal enough energy to trap it. Later, collisions or tidal stress could break it apart, leaving fragments that remained as moons. This idea is gripping because it makes Jupiter's system a museum of travelers. Comet material carries a different chemical history than rockier inner solar system debris, and it formed in colder, more remote regions where ancient ices could survive. If even a few moons have that origin, then Jupiter has preserved pieces of distant reservoirs and kept them on display in orbit. It also means the moons are not only about Jupiter, they are about the migration of material across the entire solar system, and about the moments when a wanderer became a captive. Each suspected comet fragment is a clue that Jupiter has been collecting strangers for a very long time. Others could be asteroid shards, darkened by space weathering. Some of Jupiter's smaller moons may be closer cousins of asteroids, especially in their darkness and overall character. Over long exposure, surfaces can become altered by impacts, radiation, and microscopic changes that gradually darken and re-end materials, making an object look older and more weathered than it began. If a moon started as an asteroid-like body, Kepler would place it into a harsh new environment where that weathering could accelerate. The result is a satellite that feels like a traveling rock that has been forced to adapt, its surface slowly rewritten by its new neighborhood. This possibility matters because it links Jupiter's moon population to the broader population of minor bodies that once roamed the early solar system in huge numbers. It suggests that some moons are not primordial children of Jupiter, but repurposed pieces of the solar system's construction debris. For a listener, the wonder is imagining a chip of ancient rock becoming a moon simply by passing too close to a giant planet. then being aged and darkened in place over eons. These moons are like battered passports from a time when the solar system was crowded, messy, and full of close encounters. Jupiter's moons are laboratories for volcanism, oceans, magnetism, and impacts. In one planetary system, you can study a world powered by internal melting, a world with hidden water environments, a world that shapes space with its own magnetic behavior, and a world that preserves deep time through heavy cratering. That variety makes Jupiter's moons feel like a set of different experiments running side by side under the same giant planet. The beauty is that they share a common setting, so differences become more meaningful. When one moon is active and another is quiet, you can ask what changed the outcome. When one shows signs of internal complexity and another seems more primitive, you can compare them like siblings raised in the same neighborhood but shaped by different pressures and histories. This is why scientists return to them again and again.
They are not only destinations.
They are comparisons that teach. They help reveal how gravity, distance, composition, and time can produce wildly different worlds. For a viewer, it means Jupiter's system is not a single story. It is a whole shelf of stories, each one testing a different way a moon can be alive, even without air and sunlight. Studying them helps explain how moons form around giant planets everywhere. When we look beyond our solar system, we often cannot see moons directly. Yet giant planets likely have them, and those moons could shape the evolution of entire planetary systems. Jupiter gives us a nearby template. By understanding how a giant planet can gather material, build large satellites, capture outsiders, and keep some orbit stable while others remain irregular, we learn the general rules that might apply around KOD.
Other.
Jupiter's moons also revealed that a single planet can support both companions formed nearby and later arrivals, reshaping how we picture moon systems coming together over time. This matters for large questions, including where water might be concealed, where internal heating could continue, and how satellite systems may shape rings and debris around distant giant planets orbiting other stars. In a sense, Jupiter serves as a training ground for imagination that remains grounded. It allows us to test ideas using real observations before extending them to dim, far-off worlds. The moons act as a bridge between places we can explore directly and those we can only reason about. They show that moon formation is not a single formula, but multiple pathways, and that a giant planet can follow several routes at once. Jupiter's family of moons demonstrates that one planet can host an entire universe.
When you step back, the most astonishing detail is the sheer range contained within the pull of a single planet's gravity. Jupiter gathers large worlds and tiny, irregular companions, inner objects interlaced with rings, and distant satellites living at the very edge of belonging. It holds characters that behave like separate realms, each with its own environment, history, and rules. That is why Jupiter's moons feel like a universe in miniature. They expand your sense of what a planet can be. A planet is not always a lone sphere drifting through space. Sometimes it is a central hub with its own population of worlds, its own internal geography of orbits, and its own long record of capture, collision, and change. This idea is emotionally satisfying because it makes the cosmos feel less empty. If one planet in our solar system can host such richness, then the galaxy is likely filled with similar families around other giants. Jupiter becomes a gentle promise. Complexity is not rare. Wonder
can be concentrated. And in the dark, a single planet can hold dozens of worlds, each one a different way of being real. As our journey around Jupiter slowly settles, you can let the motion fade into stillness. We have drifted past worlds shaped by fire and ice, moons stretched by gravity, cracked by tides, and quietly holding oceans in the dark. We've seen how some carry the memory of ancient impacts, while others are constantly renewing themselves, never holding the same face for long. Around one giant planet, an entire system of stories continues to turn, steady and patient, whether we are watching or not. You might imagine Jupiter now hanging quietly in space, its many moons moving like a slow constellation around it. Some glide close, bathed in energy and motion. Others linger far away, circling softly at the edge of belonging. Together, they form a rhythm that does not rush, a reminder that even the most powerful forces in the universe often work gently over time. If you have enjoyed this gentle journey, you are always welcome to like, subscribe, or leave a quiet thought below. It helps this little corner of calm science find its way to others who may need it. And if you happen to still be awake, another peaceful exploration will be waiting for you on the screen, ready to carry your curiosity a little farther. But for now, there is nothing else you need to follow, remember, or understand. Let the images soften and drift away. Allow your breathing to slow, your shoulders to rest, and your thoughts to loosen their grip. The moons can keep orbiting without you. The universe will continue its slow dance through the dark. All you need to do is rest, sleep well, and good night.